Alright, we've already considered square gates. Now we're going to do general gates. So let's review what we've done on the square gates. Let's say you had a gate that sat there. Here's the key, is this person right here. When he looks up and sees this, before what he saw was something like this. Here's the hinge and here's the gate. This was so many feet, say 2 feet across, and this say 10 foot up. But the geometry we've dealt with to this point has been only that. So now what we want to do is we want to change the geometry this person sees. Say we want, just since it's one of the simplest things to start with, a triangle. Now why would you have a triangle? I don't know, but that doesn't matter. What matters is that you have one. And say from the base up it's 2 feet, 10 foot there. Now what you notice is if you take a little dy here and you look at the d area, as this area gets smaller, the d force that comes from it, or here, is gamma times h. That's the pressure, or I could just go with pressure times d area, but we already know that the pressure is gamma h. So now the key is, as you move up and down this d area changes as you move down or up the gate. How do you deal with that? Now before, again to review before, and what made things work out so well was that the d area, as you move up and down this gate, given the fact that this dy stayed fixed, as you slid this d area up and down the gate, the d area itself was constant. Made things really easy. Now we're not dealing with a constant. So here's our problem. Our problem is you could have some sort of generic gate. Here's the hinge, and you would have some sort of d area, and as you move it up and down, definitely changes. So let's establish some coordinate systems here. First thing we'll do is we just move on down the page, and we'll just here. Alright, as we move down the page, let's redo this drawing. Make it a little bigger. Here's a hinge. Now we have our gate. Being held here. However, this person that sits down here, what they actually see is something. Here's your hinge. They see an oddball shaped. Now, like before, if you had a square gate, you weren't concerned about the distance you moved, say some distance y. Who cared? Because it didn't matter which way you moved up or down. The area stayed the same. Now you need to change this. So we need a coordinate system. So first of all, since water is, or some fluid, mostly water, is what we're mostly interested in, let's go ahead and use that. and say here's the reference location, which just happens to coincide with the top of the water. And what we'll do is we'll run a parallel line with our gate. Wherever it crosses that reference line is the origin. Now, what we'll do is, since we're interested in an area down on here, say some strip of area here, or say D area, depends on the way you want to look at it, we're going to reference down to this location. Now, it just so happens that this location sits right here on the gate, so this area right here is the same as this, just turned sideways, and it just so happens we happen to have this height of the column of water above it. So suddenly we can look at these two and say somehow h is proportional to y. How? Well, someone's going to give you this angle, theta for example, and if you look real close, all of a sudden you'll see that there is a triangle associated with that. Goes up here, back across, and back down. So with that in mind, now I can relate how y and h go together. So if this is theta here, this is also theta here, and now you have a triangle, which this is the larger side of that, and h over y, nothing more than sine of theta. Move one more step. So now I have an equation. I'm going to box some of these equations or highlight them. These equations I'm going to use several times throughout this. Let's get rid of our little guy down here. Now, as the equation was up above, this is what we're mostly interested in. I want to know what's my little d force on this little section right here. That's nothing more than gamma h times my d area. However, h is somehow related to y, and y is in the plane of our gate, so to speak. So we might want to change this to something like this: y h sine of theta d area. Now, as always, what you do is you want to integrate over the entire area here to get the entire force. So what you do is you integrate here. Now, if you integrate here, you're recognizing that you're just going to end up with the force of the water on the gate. So instead of writing all that out, I'm just going to erase it and call it just F. If that's the case, now I can just go in here and pull things out. Now, does H vary as you move A around? Now, you could say this, although we'll call it some distance D, well, not a D, but we'll call it a length times dy. So as you move y up and down, and the length here is the length of this strip right here, the green strip over here. So as you move y up and down, does h change? No. I mean, I have made a mistake here. this should be gamma. Sorry about that. So as you move y up and down, does gamma change? The answer to that question is no. As you move y up and down here, so as you move the y down or y up, does the sign of the angle change? Now this is a flat gate here. So what you're left with is this, but more. Now you'll have to determine how L is a function of y in order to do it this particular way. So I would not suggest doing it this way. I would look at that. Now, without too much thought process behind this, you'd recognize this as being something related to y bar. Now, think about it like this. If you had several strips here, what you're generally doing to find the y bar of a composite area, I'm just making up some stuff here, you sum the y bars times the area, and you divide them by, I guess I need to say total, and I need to put these as indexes. And so here's 1, 2, 3, and 4. So pretty soon what you notice is y bar times area total is equal to nothing more than an integration of y d area. And that's what happens here. You're essentially running up and down, summing a whole bunch of these green strips, and as you're summing them up, you're summing them, but here's your sum over here. It's basically turned into an integral, and it essentially yields you this result. Now, with that in mind, I'll sort of draw an arrow here and say gamma sine of theta y bar times the area total. Now I'll box this, but I'm going to take the box off in a second. So again, the key here became, what is that? And actually, what that became is this, the y bar times the area. So these two particular things are the same thing. Now, with that in mind, now I'm faced with something else that's interesting. I'm stuck with a sign in here. Now this is why I'm going to rearrange this. Now, I would contend up here, and I'll put a red, if I'm looking at h bar, I'm looking at y bar. I'm moving up the page right here. So if I put a bar over h here, here's where I'm at. If I put a bar over the h, I can just as easily put a bar over the top of the y. Let me see if I can take it back off without. Okay. So this leads me to conclude that I can simply replace this with gamma h bar area. And this is, in fact, I'm going to highlight this in yellow because this is a very important equation, and it sums the whole thing up. Now, let me talk about it. I'll put a box around it, too. As a matter of fact, I'll put multiple boxes around it. Just to make sure that we see that that's important. Now, what this is saying is the total force on a gate is only a function of total area of the gate, the distance down to its centroid, the distance from the top of the water straight down to its centroid, and then the gamma of the fluid that it's sitting in. we're going to run numbers on several gates here in a while, and we'll see that this is in fact pretty good. But that's not all the story. Now, what do you mean by all the story? Well, before you were taking a gate and you were placing a load on it, and you were actually finding a reaction load. Well, you can know this force, and that force is the same as that, but you can't find this reaction force until you know where that's at. So you need to know this distance here. Till you know that distance, there is no way to find this. So with that in mind, let's go after that distance. Now I've already have a drawing up here, but luckily from the magic of electronics I can copy the entire drawing and start back on it in a minute. So I'm going to pause the screen, and you won't notice this at all, but you'll notice in a minute the drawing will reappear. Alright, so here's our drawing reappearing back on us. Now I need to know, okay, now I'll copy down from above. Okay, there's the equation. That's the important equation. So what I'll do is I'll move this up a little bit here, and I won't even pause this while I'm moving it. Keep moving it up until, okay, so here I sit. Now I already know this. Now we have to keep in mind that we know that. But now what we're interested in is, where is this force located? Now, back in statics or something, let's just review for a second. Here we had a beam, and we had two loads. What we wanted to do was we really wanted to essentially change it to one equivalent load. How do we do that? Well, first of all, we sort of imagine. We say, I don't really care what the loads are here or here. What I want to do is I want to make these two loads equivalent to this load. Well, first of all, here's what you have to do. Okay, you got F1 and you have F2. Now, obviously, the first thing is this F3 has to be equal to F1 plus F2. Now, here's your biggest problem. Here, this needs to be D1 and this needs to be D2. It's the distance from this particular location. I need to know what D3 is. Well, pick any spot. Just so happens I picked the right end. You could pick the left end or somewhere in the middle. These two loads together must create the same moment about whatever spot I picked. Here's my spot I picked. Than this one does. So this must create the same moment that that one does, which means that D3 times F3 is equal to D1 F1 plus D2 F2. Now again, what I'm saying is, if you had, for example, let's say you had a cantilever beam. That might make it seem a little bit clearer. Here's your cantilevered beam. You know there's a moment here. Now, you got the same cantilever beam. Now, the other thing you know you have a shear there. Well, that shear is the same thing as the F1 plus F2. This shear has to be the same as F1 plus 2. This moment must be the same as that moment. The only way that can occur is if that moment itself was D3 times F3, and up here that moment is D1 times F1 times D2 F2. Now let's hold this particular thought in mind, and let's go on to our problem. Now, it didn't matter that there was one load, two loads, 3, 4, 5. There are all these individual loads. They all have to sum up to give the same moment. So I can take essentially, and that's what you did in statics, some distributed load here, take it in small chunks, and then make sure that whatever these distributed loads came up to produce this moment and this shear, that on the beam the same shear and the same moment exist. So that means this one equivalent load is equivalent to this only if it produced the same moment and the same shear on the end of this beam. Okay, it turns out that what we're looking at over in our case is more this. We have essentially a distributed load. Luckily it's not terribly distributed, but we do have it. What we're going to do is we're going to sum over these little strips to find the force, and then we're going to make sure that it produces the same moment and the same shear. Same way you did in statics. Now let me get rid of all this, and we're going to go to it. How do we sum it? Well, turns out integration is a good way to sum. So if you look way back up, you'll see, and I'll even show you where it was. Look way back up here, and you'll see this equation. Matter of fact, what I'll do, I'll even copy that equation. So here it is. I'm going to go back down the page. I want it to show up, say, somewhere around there. So I'm just going to copy the thing. And I get a little extra piece here. And then I'm going to put it in its place. So here it is. I have a little df over here. So here's my little df that occurs on this green strip. But I'm now interested in, what does the moment that it produce? Well, first of all, a moment is always referenced to a particular location. That location seems to be obvious in our case. It just so happens that it's the origin. So we're going to use y. So if I want to know the d moment, then this is a d moment from this green strip here. It's nothing more than y times df. The distance down times this strip. Nothing more than y. That's all it is. From here, I can start off. Okay, I can jump in here and do integration over this. Now, more than likely what I want to do is, instead of working with this portion, I'm going to work with this portion and that portion. Integrate that, I find the moment that gets produced. Then I come over here and I'm looking at this. Well, turns out that y and h are kind of connected. So here you go, y. Go back to my equation, which sat right here. H is equal to y sine of theta. Even write it down. H is equal to y sine of theta, meaning I can drag this through the equation and get y sine of theta. I move the gamma over in front of the y, times d area. Nothing more than gamma sine of theta y squared d area. That's all it is. This looks interesting. It's nothing more than okay, it depends on the symbol you've used before, but it's the second moment of the area about the origin. Now, I'm going to highlight that. I forgot a letter there, but I'm not going to worry about that. I'm going to highlight that because these are always related to each other in one way. What I mean by that is, where you pick your origin has a lot to do, has everything to do with the value you get out of here. If I pick my origin here, up at this particular location, which I did, then that's going to give me a different I than if I say pick my origin down here. But there's no reason to pick an origin down here because it has no real reference. This is picked because it's the top of the water. So we're going to get into that in a minute. But let's go back down and take a look at what we end up with. We end up with gamma sine of theta times I, and I'll just start writing it with the O. It's at the origin. That doesn't look very nice. The other thing we have to realize is, just like what we were doing in the beam problem, and I'll erase this in a minute. Here's our cantilever beam, distributed load. So it looks like that. What we ended up wanting to do is, of course, we want to produce the same moment, which is what we're working on. We wanted to replace it with the equivalent load, which, by the way, for our particular case, is nothing more than gamma h bar A. So in our case, this would be gamma h bar A, and we're shooting for this distance. So I can just as easily run over here and say this is nothing more than F times some Y, what they call in most books something they call the center of pressure. On our drawing, here's what it is. It is a location, say the actual load, it ends up, that's the location. The blue is maybe the location where the center of pressure is. What I mean by that, that's the location of the load. This down to here would be Y center of pressure. So it is the distance down to that center of pressure. And I'll even take this equation, move it up here, and we'll continue from over on this side. Now, what do we do next? Well, first of all, I know what that is. Gamma h bar A. Y center pressure is equal to gamma sine of theta I, which I'll leave that as IO right now. So this tells me that, first of all, that I have a gamma on both sides. And again, what we're looking for is this. We're looking to find the center of pressure. So what we want is we want to find something that's sine of theta over h bar area. Now that looks pretty ugly, but we're going to borrow an equation here. We'll just keep borrowing this equation and moving it around. Here you go. Here's the equation we're going to borrow, and I'm going to add something to it. Here's h bar, there's y bar. So that tells me that I can do nothing more than just replace that. So the y center of pressure is equal to sine of theta over y bar sine of theta area, which is nothing more than that. So the location, now I'm not done yet, but the location here of the center of pressure is related to second moment of the area about, or related to, the origin. Now we've got a problem. Our biggest problem is that is not what you're generally presented with. Here's what I mean. Go to the charts in the back of the book or in any particular book, and what you'll find is say somebody has something that's a base. They always say base and height. They always tell you where the centroid is. So they'll tell you where this centroid And somebody always says, well, what is the I about, say, XX there? And they always give you, I put a bar over that because it is the second area moment about, or let's say referenced, or relative, whatever you want to call it, to the centroid. It is referenced to the centroid. It's that simple. No one is going to put that in the tables and not reference it to the centroid because it doesn't make sense to do that. So they always 1/12 base times height to the third. That's my height, by the way. So now how do I find something that isn't referenced to the centroid? And what you generally do is you don't reference it to the centroid and you find out why, or found out how. Let's do that real quick and see what we get. I'm almost tempted to do that in a side panel or something, but I don't know that I can create a side panel. But let's say somebody set up, just did it with a square, for example. It doesn't matter what this is. I'm not even going to reference that. But let's say somebody set up a coordinate system, say y. And then somebody moved down here and they set up another coordinate system. We'll call it y with a tilde over the top. Now what I know is, or what I should know, is this thing is a distance d here. So, you know, the second moment of area looks something like that. So I can go over here and write it, I. But there should be some reference to the coordinate system because you look in here, there's a coordinate system buried in there. Now, let's go ahead and say, now let's relate something. Let's say I move up to a particular height here. Say I'm interested in this location. Now I need to redraw a few things. So I'm going to do that now. Y. Y tilde. Now suddenly I can tell you how these relate to each other. I can tell you that d plus y looks like to me it equals to y tilde. So now let's make use of that. So here's what I'm saying. I can move this red line down or up anywhere. As I'm moving it down or up, eventually I'm going to come across this surface right here. And what I of course want to do is I want to integrate this little d area here. That's what you got sitting right there. So as you do this, you're integrating d area. I just so happened that it didn't look right, so let's change this up. Let's change this. I'll make this thing look more like this. Here's my object. Doesn't look very good. Matter of fact, maybe I should move it over. Now, this is reference to the centroid. We need to remember that. This is reference to the centroid. Redraw my funny object. Okay. Try this again. Now, this little red line is associated here with this D area here. As I move this red line, and you want to move it up, you want to move it down until you sum over the entire area. That's what the integration means. So then you go down through this thing and you say, well, what is y? I want to know what the second moment area about this location is. I'm putting these little X's here because that's my reference location all along in here. You want to make it accentuated? Let's make it a blue line here. That's what I want to know. So I really want to know this. Now, is that all strange? No, not really, because if you look at it, this is not the centroid. This line, this reference line, is not the centroid. It's not the location of the centroid. Through the derivation, I came out with a second moment of area that was related to that. Now I'm back in here doing this. This location is not the centroid. This is. So I contend it's nothing more than, and I need to square this. So I need a little bit more space. Let me rewrite it, back it up a little bit. Now I'll square it. Nothing more than that. Sorry about that. Hope that didn't bother you there for a while, but if it did, you'll get over it. Now, if you look at this again, you get integration of d squared, d area, plus 2 times the integration of d times y, d area. Maybe it'd be better to write it as a y times d, because that d is just this distance here. And then plus an integration of y squared d area. Now, take a look at this. D doesn't change with area. It's a fixed distance. This distance right here is fixed. Doesn't change. Nothing more than d squared times area. Plus, what do you do with this one? Well, first of all, d was fixed. I can pull it out. Plus, this looks interesting because y is referenced from the centroid. This is nothing more than what you see in the tables. This is nothing more than d squared area. What is that? If you think about it, this may take a minute. I'm going to ask you a question. Somebody gives you this box. They say, I'm going to place the origin at the centroid. What is the y location of the centroid? What is y bar if in the coordinate system in which I place y at the centroid? By the way, this integration is directly related to that, with an area, of course. So the question I have is, who's buried in Grant's tomb? What is the location of the centroid when I place the origin at the centroid? The answer to that question is, that's 0 by definition. So, who's buried in Grant's tomb? I don't know, but I hope it's Grant. So, what you end up with is the parallel axis theorem. I of any location is equal to the I at the centroid plus the distance you move, the distance between this location and that location, times the area of the object. Now, hopefully that all made sense. Now, if you did that, what you find out, you can run back to your equation and you could say, well, what is this? Well, it's nothing more than, and now you have to think about this, What I have in that equation is this. What is this and what is that? I bar plus some distance squared times the area over y bar area. Now, what is this distance? What is the distance from the location that references this, in effect the origin, to the centroid? What is the distance from the origin here to the centroid? Well, not too surprisingly, that looks nothing more than y bar squared in our case. So now I'm running into some space issues, so I'm going to move some things around. I'm going to compact my equations a little bit. And I'm going to come up with my final answer here, which is, and if you look at this, I need to also compact or move this stuff down as well. So I'm going to take off and do that. It didn't work. I'll just try to do the best I can. So with this, I end up with y center pressure is nothing more than, notice that this looks the same. I mean, I have just simply y bar plus the second moment of area about the centroid over that. So you can look at them for a minute, but let me move this down. And I'll tell you that this is a highlighted equation as well. These two equations, this one and the one above that I'll talk about in a minute, are the two equations that get you through all the problems. The location, okay, let me try to emphasize this. The location on that drawing to the load is the location to the centroid plus some delta. And that delta is I bar over y bar area. Now let's work a problem so that you'll see this to be working out to be the case. Let's take the problem you should already know the answer to. I'll draw a blue line across here to show we're actually working a problem with numbers. And it's a problem that you've seen before. Make my life easy. I'm going to make it 45 degrees. Here's my water surface. There's the free surface. Here's my dot 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 over to my origin, which sits right there. Here's the piece of concrete that is holding the load. My eventual problem is to find that reaction load there. Now let's start working the problem. 5 foot. Let's say it's 5 foot down to the hinge. Let's say 45 degrees. Make my life easy. Let's say this is 10 foot here. However, we need to identify the profile of what the gate looks like. We're going to make it look like the gates we've seen before, just to make our problem doable two different ways. So here, in fact, is our gate. Let's move that a little bit. Here's our gate. We're going to make it 1 foot deep here and 10 foot high. So this person sees a little strip gate right there. Now you know how to work the problem the other way. Now we're going to find out how to work it this way. Gamma H bar A and Y center pressure minus, now yx minus is this. I'm moving the y bar over, so y center pressure minus y bar. And I'm going to call that a delta. Is that y bar area, which is this equation. So these two equations, and that is all I need to solve this problem. The value of the load, the location of the load, and I'm just going to locate it related to a delta, and I'll use it on the drawing. We'll find out what that is, so it makes better sense. Here's my origin. There's my y. Here's my y down to the centroid. Now, this number is a delta. Y center pressure minus y bar means that this number is simply the distance below the centroid that the center pressure is located at. And that's all it is. So if I draw my y down here, this is y center pressure. Y center pressure is always greater than y bar. Now, if you had a gate that was sitting flat on the ground, then essentially the load would be uniformed, and guess what would happen? The equivalent load would look like right at the center, meaning that y center pressure equal to y bar. Now let's say we tilted the gate up just a small amount. Let's tilt it up, very slight amount. So it's tilted up. And guess what? You have this load, but because it's tilted up, it has a slightly greater pressure at the bottom than it does at the top. Meaning, like you saw before, you had a force that is related to this area, and that gives you this force, but you also had a tiny force related to this triangular area, and that tiny force was moved 1/3 of the way down, meaning that equivalently there's one load, that is the addition of these two forces, slightly shifted below the centroid. As you tilt that gate further and further, you increase this value, this lower pressure, until you get it to the point that it becomes fairly large. And you shift that even further down. So if you see what I mean, again, this is because the depth of this location is lower than the depth of this in the water, meaning the pressure is higher down here than it is up here. If that's the case, you end up with this little load that's 1/3 of the way over. That's why, if you look at these, what you'll find is you'll find that center pressure always greater than or equal to y bar, meaning that if the gate is flat on the bottom of the ocean, that they equal. You start tilting it, they start moving away from each other. What was nice here is if you reference this, then the distance between these two is nothing more than the delta, which is why I like to reference it this way. So let's take off and find the problem. What is the force? What is the total force on this gate? Well, before we start listing this, let's identify everything in this equation we need to have. I see that I need to know gamma. I see that I need to know h bar, area. There's area. I need to know y bar, and I need to know I. So I need to know 5 things, and if I know these 5 things, I can simply substitute in here. So let me go over here, and I'm going to do it over here because, well, I'll do it right there. Here, let me change my handwriting, make it a little bit better. I'll tell you, it's 62.4 pounds per cubic foot. Now I'm going to tell you that area. Well, the area of this thing is a 10 by 1, so it's a 10 feet squared. About the centroid, that is. Now, in some textbooks, they'll list it this way. In other textbooks, I think they list it this way. It doesn't matter. It's the same thing. 1/12. The base, in this particular case, is 10. I'm sorry. The base is 1. And 10 is the height of this thing. The height goes in this particular direction. Now I'm going to have to relate to my calculator. And what I end up with is 83.3 or 83 1/3. How about I just write it like, well, 83.33. Good enough. Now I need to know H bar and Y bar. Now this is where geometry comes into play. I guess a little geometry comes into play here, but it's not as difficult. Okay, I need to know. And what I'm going to do is I'm going to slide my 10 out of the way and come back and reference. Okay, this drawing is not that great, but apparently if you come up to this location, that doesn't look like the centroid, but it is the centroid. So this is H bar. That means that I've already got Y bar in here, so let's look at the triangle here. We come straight down, come back up, and back across. There's my triangle sitting there. Well, I've got parts of these things already figured out. So I'm 5 foot down to here, and I know the distance from here to here. That's 5. Because this is 10, that's 5. Well, that's annoying because here I've got another triangle. I've got this triangle. Comes across. So it depends on the way you look at this. Here's a value that I do not know, which I can find. And if you want to look at another triangle, let's look at this triangle. They all look the same in one way. They're all 45 degrees. And depends on the way you want to look at things, but here I don't know that value. But I can tell you if I find one of these, it's pretty easy to find the other. So I would contend that if this is 5 foot from here to here, that's got to be 5 foot from here to here, because this is 45 degrees. And this distance would be what? 5 squared plus 5 squared is equal to 5 square root of 2. So I don't know what that number is, but that helps me because what it tells me is that tells me that I can find, say, Y bar first. Y bar is nothing more than 5. And what we're looking for is this value. So I'm looking for 5 plus this value. 5 plus what? Whatever that value was. Hang on, give me a second. Plus, now that value is that 5 square root of 2. Let me grab a calculator. That number ends up being 7.0710. Yeah, 7. There you go. That's good enough. Now, depends on how you want to find the other one. One way is just to use the equation, which was way back up. I guess it was way back up here. Here. You could use this equation. We'll lasso it and copy it down there. So if we want to use that equation, there's nothing wrong with using that equation. So I can just say h is equal to 7.07107 times sine of 45 degrees. That's given, of course, that you turn that into a bar. Oh, did that wrong. No, that's okay. I've got an error there. And the error there was I did not add those up. Meaning that this value is actually that. And I needed to add 5 to that, which ended up being, 12.07107. Good enough. Which means that this ends up being 12.07107 times sine of 45. Means I end up with about 8.5355. Good enough. Now, with all that, here, let's just go ahead and erase this. Now, I don't need it. I know I copied it, but it doesn't matter. So now let me highlight what I need. Let me go back and add that. Those 5 values. And I need them in those 2 equations. So, go back and say, here, let's... F is equal to gamma h bar area. Nothing more than, where's my gamma? It was 62.4 times h bar. Apparently 8.5355. And then area was just 10. Okay, so if you take a look at this, you end up with 5326. So the force is equal to 5326 and change. Now the delta, I bar over y bar area, and I end up with 83.33 and several other 3's. Y bar of 12.07107, an area of 10. So 83 point bunch of 3's divided by 12.07107, and divide another 10 into there, and so I get a number of about 0.69 and some smaller other numbers. What does this mean? Well, here's what it means. I have a gate. It sits there. Now, here's the centroid referenced of 5. I move down this value, delta, and put a load of 5326 here. Here's my reaction load. So my reaction load is equal to 1/10, because this is 10 foot. Remember, this, the moment about the hinge has to be the same. 10 times r is equal to this distance times that. 5326 times 5.69. Where'd the 69 come from? Right there. Where'd the 5 come from? Distance down to the centroid. So 5326 divided by 10 times 5.69, roughly, the reaction load is roughly 30, 0.5. Now, are we right? I don't know. Let's take a look here. Let's do it the old style way. What's the old style way? Hey, here we go. The old way is take this gate and put the equivalent load on here. Now this is what we learned last week. Got a gate sitting here at 45 degrees. We've got a uniform load across it, and we have an additional triangular load because this end of the gate is deeper than that end. What is this load? Well, let's look back. It's 5 foot deep. So it's 5 times 62.4. That's the pressure there. 5 times 62.4 gives me 312 pounds per square foot. How much deeper is this end than that end? Well, so that means what's that distance? Well, turns out if you've taken this number, square it, and that number across the top of the purple, square it, those two squared. Okay, so in other words, let's call this z in z. Z squared plus z squared is equal to 25, or 5 squared. So that means z squared is equal to 25, or z is equal to 25 over 2 square root of that, or 5 divided by square root of 2 gives you 3.5355. Now, do you notice anything looks like that in here? That is that number minus 5. Add 5 to that, our value there, and you get 8.5355. Same thing as this. So this value is 3.5355 times 62.4, or 220.617. Okay, so just like that, you've got two loads. This first load is 312 pounds, but over 10 foot. So it's 3120 pounds right there in the center. This load is 220 pounds times 10 and then divided by 2. 220.617 gives you 1103. 1103. Now 1103 plus 3120 gives you not the right answer. All right, I see what happened here. This value is the incorrect value. What I needed to do is I needed to go to the end of this gate. pressure at the tip end of that gate is not just 3.5, it's 3.5 times 2. That moves me to the centroid. I need to move all the way down. So what I have here is an incorrect value there. What I'm saying is, okay, let me see if I can recorrect myself without editing this video, because I don't want to do that. Previously I found the distance here, z. Actually, that distance is the same as another purple triangle like that, because this is 5. This is another 3.53. So that means that this value should be 2 times that, or let's see if I can fix this. 2 times 3.5355 times 62.4 gives me this value, 441.23, which means this gives me 441.23 times 10 divided by 2 gives me 2,206 pounds. So that value is 2206 roughly. Now the first key is, do this number and that number is the total load here. Do they end up being, or what do they end up being? Okay, 2206 plus 3120 gives you 5326 pounds total. Now I haven't found the location, but what you'll find here is 5326. 5326. You have 2 ways of working this now. Now let's sum moments about this hinge. Okay, reaction times 10 has to equal 2206 times this distance is 2/3 of the length, or 10, 2/3 of 10, plus I have a 3120 pound, and that's only 5 foot, times 5. Reaction, 10 times the reaction is equal to 2206 times 2 divided by 3 times 10 plus 3120 times 5 gives me 30306. And if I divide by 10, then I get 30, about that many. It's just drops of change. And that and that, well, I guess I should carry the 0.6 to make it. That and that end up being same numbers. So we can see that for a square gate, either one of these works. And on the test, that's what we're going to deal with, this square gate. We're going to come back and take a look at this, and I'm going to also give you possibly a problem that's impossible to solve with, not impossible, but incredibly difficult to solve this way, which leaves you back to solving the problem using these simple 2 formulas right here. And with that, all you got to do is find 5 variables and understand the geometry that you're dealing with. And with that, I'll call this lecture done.